The technology of wide field, faint, sharp telescope imaging has allowed us to survey billions of stars to map out their brightness and their colour. Now, you'll remember that I sketched out a Hertzsprung-Russell diagram for you, and what I want you to do is to take a moment now to think what that diagram is going to look like if we plot over the data from all of these stars. Now, are all stars like our Sun, and therefore they'd live here on the diagram? Or maybe stars are just random brightness and random colour, and they just live randomly all over this diagram. Or could it be that there's a preferred combination of brightness and colour, and that we'll find all the stars live along a preferred region in the diagram? So this is the Hertzsprung-Russell diagram of all the stars in Omega Centauri, and the axes here, let's remind ourselves, are brightness and colour. Now we can see that there are preferred combinations of brightness and colour where different groups of star lie. The majority of stars are lying along a band that we call the main sequence, and this is indeed where we find our own Sun. Now some other stars are found at brighter luminosities and redder colours, and we call these the red giants. Over here we see the bright blue branch stars, and there are also some low luminosity blue dwarf stars down here. So the Hertzsprung-Russell diagram is evidence that stars are changing and evolving, and the different groups that you can see in the diagram are stars that are experiencing different physical processes going on inside them. Now, our theories about what's happening inside different stars are all based on a long battle that happens between gravity and pressure. Now, gravity is trying to pull the stars together, and pressure is resisting that squeeze. Now, in our own Sun at the moment, the forces of gravity are perfectly balanced by pressure. At the core of our Sun, the temperature is hot enough for a nuclear fusion reaction to take place that turns hydrogen into helium. And one of the byproducts of this reaction is the production of neutrinos that we can detect as evidence that this reaction is taking place. There are about 50 billion neutrinos flying through your thumbnail every second, produced by our own Sun. Now, how can this reaction produce light? Well, to answer that question, we're going to use Einstein's famous equation, E equals mc squared. Now, the fusion reaction that's going on in the centre of the Sun fuses 4 hydrogen together to make helium, some positrons, and some neutrinos. Now you can look at the difference in the mass at the start and the end of the fusion reaction, and the difference in mass is about 4 times 10 to the minus 29 kilograms. So the energy that's produced in each one of these fusion reactions is just the change in mass times the speed of light squared, which is 4 times 10 to the minus 12 joules, or 1 trillionth of a peanut. It doesn't sound like very much, but there are 10 to the 38 of these reactions occurring every second inside the Sun. The Sun's essentially turning mass into energy. Now, if we have a more massive star, then we expect there to be more gravity and more fuel to burn, so we'd expect those more massive stars to shine brighter and hotter and more bluer. So let's go back to the Hertzsprung-Russell diagram, and you'll see this is exactly what we find. Along the main sequence, we find a range of stars of different masses, and as we get to more massive stars, they get brighter and bluer, exactly as we'd predict from our theory of nuclear fusion. Now, at some point, the fuel bank is going to run out. There's not going to be enough hydrogen in the centre of the stars to keep powering this nuclear fusion reaction. And it's at this point that we see a change in the brightness and colour of our star. Indeed, this is going to happen to our own Sun in about 5 billion years' time. The hydrogen in the core is going to run out. Gravity is going to win that battle. It's going to pull the
the gas inwards into a hotter, denser region, and that's going to ignite a shell around the core, and a new nuclear fusion reaction will take place.
And what happens then is that heats up the outer envelope, which increases the pressure, and that envelope expands and grows bigger and bigger and redder, and you'll see that on the HR diagram. Those red giants, they're very luminous, they're very bright, and they're also red.
That's going to happen to our own sun in about 5 billion years' time. It will go out at least to the orbit of Earth, probably even further, and will it or won't it consume the Earth? Nobody knows. So as the gravity-pressure battle plays out in the life of our sun, more complex reactions are going to occur in the core of the sun. It's going to fuse helium into the carbon that your body's made out of, and into the oxygen that we breathe. There are going to be pulsations through the stars that throw off the outer layers, producing these spectacular planetary nebulae that you can see right now. Now, for the most massive stars, the cores are such a hot, dense environment that the chemical reactions are going to fuse together the heaviest elements in our universe. And in these final death throes of these stars, they're going to explode in what we call a supernova explosion. And you can see that on the picture here. Now, one day these chemicals will be pulled together again by gravity. It's going to form new stars, planets, and maybe even new civilizations. Now, if you're in the Northern Hemisphere, you're going to be able to see this happening today in Pleiades, which is otherwise known as the Seven Sisters. Now, by astronomical standards, it's a relatively new cluster of stars, and you can still see some of the gas that the stars were made from about 150 million years ago. So without stars, the chemicals that you're made up of simply wouldn't exist. It's true, we're all made out of stardust. And I hope by the end of watching these videos, you now understand the science and technology behind this major astronomical discovery.